All right, today we're going to crack the code on something that, completely changed how we build software. We're talking about object-oriented programming, or OOP for short. And you know what? It's pretty much the only reason our massive digital world doesn't just fall apart. So let's dive in and see how it all works.
Really, have you ever stopped to think about it? How in the world do developers build something like a massive video game, or even the operating system on your computer, with millions of lines of code, and not have it just completely collapse into chaos? How do they keep it all working, stable, and even update it? It sounds, well, kind of impossible, right?
Well, guess what? The secret isn't some kind of magic. It's actually a really brilliant way of thinking. It's a whole new approach that took all that chaos from huge software projects and just brought a logical, super intuitive order to everything. And yep, you guessed it, that big idea is object-oriented programming. Okay, so to really get why OOP was such a game changer, we kind of have to travel back in time a bit. We've got to understand the world before it existed. Let's take a look at the exact problem it was built to solve. So before OOP came along, the main way people coded was called structured, or procedural programming. And the focus was all on doing things. It was a list of actions, right? Procedures, algorithms. That was the name of the game. Now, the data? Well, the data was often just sitting out in the open, globally, where any part of the program, any function at all, could just reach in and change it. And look, for small, simple programs, that worked just fine. But the second project started getting bigger. Oh man, it became a total nightmare. Imagine functions all over your code, just randomly reaching in and changing that same shared data. What you ended up with is what programmers famously call spaghetti code. It's a perfect name for it, right? Because everything's tangled. You'd change one little thing over here, and it would cause this totally unpredictable, disastrous chain reaction somewhere else. The code was fragile, it was a mess, and trying to fix or update it, forget about it. So, yeah, this whole spaghetti code thing was becoming a real crisis. A breaking point. Programmers desperately needed a new way to think, a complete shift in how they approached code, something that could actually handle this new level of complexity. And right on cue, this is where object-oriented programming steps onto the stage. And here's the big idea, the thing that changed everything. OOP completely flipped the script. Instead of starting with a long list of actions, it made programmers ask a totally different question. What are the things, the objects, in my program? And the revolutionary idea was to create these little self-contained digital objects that bundle their own data together with the code that works on that data. Suddenly, the data and the actions weren't separate anymore. They were locked together. You see, that shift in focus was the absolute key. A program wasn't a list of instructions anymore. It was a collection of little objects all talking to each other. And, this is so important, an object's data was hidden, protected inside of it. You could only get to it through specific, approved channels. This meant objects could communicate without showing off all their messy internal wiring. And that right there, that's what stops the spaghetti code. So, what does it actually mean to think in objects? Well, let's break it down. It really comes down to two fundamental building blocks that make this whole thing work: classes and objects. Okay, first up, you've got the class. Now, a class isn't the actual thing. It's the blueprint. The best way to think of it is like the architectural plan for a house. The blueprint tells you everything you need to know, how many rooms it'll have, what it's made of, and it also defines what you can do with the house, like open doors or flip on the lights. And then you have the object. So, if the class is the blueprint, the object is the actual physical house that you build from that plan. It's a real, living, breathing instance. And here's the cool part. You can build lots of houses, lots of objects from that one blueprint, but each one is its own unique thing. One house might be painted blue, another one red, even though they came from the same plan. Let's use another example to make this super clear. Let's talk about a car class. The state of the car, its properties, would be things like its color, its model, maybe its current speed. And its behavior, the methods, would be the actions it can do: accelerate, brake, turn. So now every single car object we create from that one car blueprint will automatically know these things and be able to do these actions. And this is how OOP makes complex systems manageable. You can take a huge real-world system, like a bank, and just model it as a collection of objects. You'd have customer objects, account objects, transaction objects, and they'd all interact with each other in very specific, defined ways. It's just a much more natural and intuitive way to represent the real world inside your code. All right, this whole powerful way of thinking is held up by four main ideas.
People call them the 4 pillars of OOP. Honestly, you can think of them as the superpowers that make this entire system work. So, let's break them down, one by one.
First on the list is encapsulation. This is basically the idea of putting a protective bubble, a capsule, around an object's data. You bundle the data and the code that's allowed to touch that data together in one neat package. And what this does is stop other random parts of the program from just reaching in and messing things up. It's your #1 defense against spaghetti code.
Next up, we have abstraction. This one's easy. Just think about using an ATM. You know you can put your card in, punch in your PIN, and get cash out. But do you have any idea what's happening on the inside? How it's connecting to the bank, verifying your balance? Nope, and you don't need to. That's abstraction. It hides all the complex, messy details and just shows you the simple stuff you actually need to use.
Third pillar, inheritance. This one is all about not repeating yourself. It's about code reusability. It lets you create a new class that just inherits all the features of a class that already exists. A really good way to think about it is an is-a relationship. For example, a programmer is a type of employee. That means we don't have to rewrite all the basic employee code for name, ID, salary, and all that. The programmer class gets all of that for free from the employee class, and then we can add the special stuff, like a write code behavior.
And last but not least, #4, polymorphism. It's a fancy Greek word that just means many forms. And in programming, it's this super cool ability to have one command do different things depending on the object. So, for example, you could have a cat object and a dog object, and you tell both of them to make sound. What happens? The cat meows and the dog barks. See? Same command, but you get different, appropriate results. It makes your code so much more flexible.
So when you put all 4 of those pillars together, encapsulation, abstraction, inheritance, and polymorphism, what you get is a set of incredible advantages. Advantages that directly solve those huge problems we talked about at the beginning.
So let's just tie it all together. Remember that tangled, fragile spaghetti code? Well, encapsulation gives you data security to prevent that. Sick of rewriting the same code over and over? Inheritance gives you amazing code reusability. Feeling overwhelmed by complexity? Abstraction makes everything so much easier to maintain. It all works together to let us model the real world in our code in a way that just makes sense, and more importantly, a way that can scale up without falling apart.
And just to give you an idea of how fundamental this way of thinking is now, just look at a language like Java. One of its core principles from day one is that in Java, everything is an object. For a ton of modern programming languages, OOP isn't just some nice feature, it's the very ground they're built on.
So at the end of the day, remember this. Object-oriented programming is so much more than just a way to write code. It's a powerful way of thinking. It's a mental model for breaking down huge, complex problems into small, manageable pieces. And that leaves me with one final thought for you. What's a problem in your world, big or small, that you could maybe understand a little better if you started thinking about it as a collection of interacting objects? Give it some thought. Thanks so much for tuning in.